crazy? It's Christmas Eve. It's the one night of the year when we all act a little nicer. We smile a little easier. We share a little more. For a couple of hours out of the whole year, we are the people that we always hoped we would be. It's a miracle. It's really a sort of a miracle because it happens every Christmas Eve. And if you waste that miracle, you're going to burn for it. I know what I'm talking about. You have to do something. You have to take a chance. You do have to get involved. There are people that are having trouble making their...
Okay, we're looking at today's lesson, and, well, what is that lesson? Well, I'm going to show you in a second. So, we're looking at your virtual content, and you are going to do the assignment. I'm going to show you that in a second here. Again, this is my apps, the links you have. This is what mine looks like. So I'm going to go to Virtual SC. Okay. Well, actually, let's do this. I'm going to go to Google Classroom. Well, that's a little better avenue. All right. Go to Chem Honors, and as you can see, you have an updated, revised Chem, calendar. So if you open this up, it should look like this. As you can see, December. I'm going to blow this up so it looks a little better there on your screen. Let's try that again. Okay. So as you can see, we're in December. Happy December. It's December 1st. Hopefully you're ready to go. Today is Wednesday, the 1st, and we have the 11.2. Well, let's click on that. And if you notice ahead here, next week we have final exam reviews from December 8th, 9th, and 10th, and you have 13th and 14th. That's 5 days of final exam review. So Unit 11 does not have a test. We're rolling that into the final exam. So now our dates for the final exam are 15, 16, and 17. You can choose to take that either day of those three. The 20th and 21st are e-learning days, technically, if you have makeups to do. That's a good time to do that. So that's good. We got that all taken care of. That's been emailed. That's been put in Remind. That's been put in Google Classroom. So really there's no excuse. Let's go to 11.2 without further ado on this. So if you notice here, we have the 11.2, the first law of thermodynamics. And the first law of thermodynamics is you do not talk about thermodynamics. The second law of thermodynamics is you don't talk about thermodynamics. That's a reference to a movie called Fight Club with Brad Pitt. So we're going to go ahead. I'm going to move forward with this and see if I can blow that up again. Let's go to 100%. Look at that. So the word thermo, of course, means heat. Heat meaning, heat. Dynamics meaning change. So, the dynamics of something could change, like our calendar. Thermo, heat, changing. The first law states that energy cannot be created nor destroyed. We'll explore transformations of kinetic energy and reactant bond energy, basically potential energy, and product bond energy. So by the end of this lesson in 11.2, you should be able to draw and label the parts of potential energy diagram. Create potential energy diagrams from enthalpy information. Write thermochemical equations. Determine change in enthalpy and activation energy from a potential energy diagram, and determine whether reactions are exo or endothermic. Whew. All right, based on potential energy diagrams. That was a mouthful. All right, so again, average grade taken. So let's preview the quiz now. You'll see you have several informational pages and only six questions. So a lot of information to go over. And perhaps, I would assume, enthalpy might be a new word. How much stuff is in there as far as heat? How much heat is in the heat content of something? Enthalpy. An endothermic reaction, we know that energy or heat is put into a reaction. The potential energy is positive. Exothermic, okay, a reaction that has potential energy difference between the products and reactions that is negative. So we're looking at numbers here. Endo, we have a positive potential energy. We have a negative potential energy in exo, releasing something, so we lose it. You lose something, you become more negative. It's like you lose electrons in an equation. The charge becomes positive, but that's almost the opposite. But but something else gains it. Heat of a reaction, change in enthalpy of a reaction. Delta H is always change in heat or enthalpy, because its enthalpy is heat content. We're looking at the change in enthalpy. That's delta H. I see this is going to be a tough morning for pronunciation. Internal energy means inside energy. Total energy contained in a thermodynamic system called enthalpy. Heat is H, and you can use H as enthalpy as well because it's heat content. Okay. Potential energy diagram, and this will show the potential energy changes during reactions and reactants to products system. The reactants and products and reaction, basically. That's the system. Okay. I don't know why they duplicated it almost verbatim to what does that mean. But the last one is thermochemical, heat chemical reaction equation. Thermochemical equation. That's an equation that includes the enthalpy change of the reaction. That's a delta H. Gonna go to the next page. We must first look at potential energy diagrams. And what are you looking at here? Well, here's the y-axis, that's increasing potential energy. The x-axis is below here. That's reaction progress moving along. The reactants here, you can see the potential energy is higher than the products. That's basically change in enthalpy. Alright, then we have it moving along the reaction. We have, of course, that moving, the change in delta H from here, here, here. You can imagine if you took calculus, you would have basics in, the area of the graph in certain areas. Alright, so, and we have the product. So it looks like that's a negative potential energy. So, every system or sample of matter has energy stored in it. Okay. When a chemical reaction occurs, the new bonds are formed never have exactly the same amount of potential energy as the bonds that were broken. Okay, so some of the bonds are broken and reformed. Synthesis, we have different single replacement, double replacement. So are the bonds that are broken releasing energy more than the bonds that are formed and storing the energy? Therefore, all chemical reactions involve energy changes. Energy is either given off or taken on by the reaction. Potential energy diagrams, which is this, illustrate the potential energy or stored bond energy of the reactants and products of a chemical reaction and how this energy is. And where was I? Another announcement happening. Potential energy diagrams illustrate the potential energy or stored bond energy of the reactants and products of a chemical reaction and how this energy changes during a reaction. That's a mouthful again. So, but they illustrate potential energy. We're starting with potential energy of the reactants up at this level of how much energy you have, increasing upwards. Or stored bond energy. So there's a lot more being stored here in the reactants energy. Okay, and the products of the chemical reaction, how the energy changes during a reaction. So potential energy up here, and as you get to the products, potential energy down there. So it's a negative or a subtracted loss of energy or transformed into something else. Take a look at the potential energy diagram, the way we did that. Okay, and we know the y-axis represents the potential energy. Okay, and that's the amount of energy required to, the bond energy is the amount of energy required to break a chemical bond, is also the amount of energy released when a chemical bond is broken. When we talk about potential energy, we're talking about the energy stored within the bonds of reactants and products. The potential energy is part of an internal energy. And these are definitions. Internal energy represents the total energy of the system called enthalpy. Okay, delta A enthalpy. That's how much heat content is there. and that's internal energy, is what's in that the energy contained in that whole equation reaction, or the movement of the reaction going forward to the products. It's contained in that system. The reactants have a certain enthalpy content of heat, and the products have certain enthalpy. So the reactants and products, different enthalpy, or whatever. The energy doesn't really. You're looking at the change now. The change of enthalpy reactants versus products is represented by delta H, or the Greek symbol means change. You can have delta T, delta H. You can have all kinds of deltas. The x-axis in the potential energy diagram, of course, we know the reaction progress. When chemical reactions proceed or are read from left to right, they are called forward reactions. Looking at the potential energy diagram, reactants for the forward reaction are found to the left in the diagram, and the products to the right, as they should. And you know what a normal reaction looks like. We studied equations and how to balance them and how to read them and what types there are. When the diagram is read from right to left, it is called the reverse reaction. All right. So right to left, left to right, the reverse reaction. Sometimes you'll see equilibrium symbols, an arrow, a half, bent arrow, and another one going that way, half bent. It's an equilibrium reaction. So you can go either way. Okay. And where are we at here? Of course, I lost my place. When the diagrams, we have that. All right. The enthalpy of a substance is called the heat content. We know that from our definitions. It's a knowledge-based level of learning. The potential energy stored in bonds of a substance can be thought of as heat stored as potential energy. When the bonds are broken, as is released, the heat content of the products with some heat, either lost to the environment or absorbed. I love that. Or absorbed. All right, the enthalpy of the heat content, or enthalpy of the reactants and products, is almost never the same. Almost. There's that word. And for the true or false questions, whenever you see never without the almost, almost is always, and never are almost always false. But therefore, when a reaction occurs, there is a change in the amount of potential energy. Of course, we saw that in the diagram. Stored in bonds, the reactants and the products, betwixt. If the bonds of the product stored more energy than the bonds of the reactants, then energy must be taken in during the reaction. If the bonds of the product store less potential energy, then the bonds of the reactants, then the excess potential energy will be left over and will come out of the reaction as kinetic energy. So we're transforming potential to kinetic. And that is a negative loss of energy, but it's transferring to the law of conservation of energy can't destroy it or automatically, it goes away somewhere. It's a law. It's always proven right. Difference in enthalpy, difference in the heat content of the reactants and the products is expressed as delta H. You can have a negative delta H, or the change in enthalpy. Since this is either taken in or given off during the reaction, is called the heat of the reaction. A lot of heat thermal stuff. Let's go to the next page. Okay. Let's see if I can make this, the old full screen thing. Yep. All right, so exo and endothermic potential energy diagrams. I've been kind of alluding to that already. So you've heard me say this. Things leaving the system to kinetic energy, or coming into the system. Endo. Okay, let's look at these things. Two types of potential energy. These two types center on the difference between the energies of the reactants and products. So there's differences here. Reactants, products. There's some different energies there. Up here, down there, down here, up there. So you see the delta H changes between those two. The figure below, or the picture below, an endothermic reaction is shown on the left. So heat is put, technically, enthalpy content increases from reactants to products. All right, so boom, down here, potential energy increases Boom. Now here, of course, they're going to say up here, the exothermic reaction has given off that enthalpy from the products, because you have a negative product energy that gives off into kinetic energy. It doesn't just go away, it transforms. Delta H, of course, is heat content. We've kind of, done this. And how do you calculate delta H? That is a variable you're solving for. The heat content of the products, not the content, but the heat product of the content products, and then the subtract in the reactant. So you take the products, you subtract the reactant, whatever this number is on these graphs. Okay, not 0, of course. 0 is down here. When enthalpy of the reactants is greater than the enthalpy of the products, the heat given off by the reaction, delta H will be negative. Okay, so if you see a graph and you see the delta H's represented by numbers, you'll know probably the question will be which of these is an exo or endothermic reaction. Now the opposite is true when the products is greater than the enthalpy of the reactants, like this one here. I wish I had a little pointer. Of reactants as shown on the graph on the left. Boom. If the difference is greater than 0, the energy is considered to be endothermic, which is going to be the graph on the left. Alright, so that question in the graph, which one of these are representations of endothermic reactions? It's the positive one, greater than 0. Alright, kinetic energy is absorbed and becomes potential energy or bond energy in the products. Alright, so less than exo, greater than is endothermic, and that's then 0, of course. Excess potential energy from the bonds is left over and is released into the surroundings as kinetic energy or heat. It should be clear that to you that the reverse reaction of exo is going to be endothermic. All right, and you have an equation here. This equation below represents a chemical reaction where energy is produced. This means there's less energy stored in bonds in the products than there is in the reactants. Okay, this is, of course, less energy is given off. That's an exothermic reaction. Extra energy is released in the surroundings when the reactants become the products. The release of energy is indicated by a negative delta H. So we have this reaction here, sodium chloride, okay, silver nitrate, and we have this becoming silver chloride, and then that is going to be Na sodium. Hold on, I have to look at the numbers here. Yeah, so, it's right here. Delta H is negative 166 kilojoules, 166 kilojoules, and less than 0, so we know what that means. It says it up here. Less than 0 is here. That's an exothermic reaction, and you can tell that by the graph on the left. I'm sorry, the graph on the right, exothermic. In comparison, the decomposition of mercury oxide, mercury 2 oxide, that's transition, requires a net input. So we have an input, endothermic, as a positive 181.7 kilojoules. Okay, and there is, of course, your basic video. That's a long video, 25 minutes. And this lecture is going to be long too, so I'm not going to extend it for 25 minutes. And this talks about some of the things we just talked about in different examples. See how long that is? Holy cow. So do look at that, though, in your own time. It'll help you with the final exam. All right, the barrier, the threshold energy. You're looking at this threshold. Reactants here, potential energy. The threshold energy is really small to get this to go. All right, this is low. Here we got a lot of some activation energy or threshold energy in this, and we of course have the delta H content, change from here to here. And as you know, this is exo, and this is going to be hugely exo, and that losing a lot of energy into kinetic energy. That's your threshold energy represented by the red areas. Of course, your delta H is a change in enthalpy. Okay. When a reaction has a low activation energy, as in the figure A, most of the reactants in the molecules have a sufficient kinetic energy to react. And the reaction will most likely be rapid, a high reaction rate. Okay, progress moves along pretty fast. When a reaction has a high activation energy, as in figure B, over here, most of the reactant molecules will not have enough energy to react, and the reaction will most likely be very slow. Alright, we need to pump in that energy, and it takes a while to do that. Imagine the ATP molecules to make some things go in your bodies. And where are we at here? How much do we? All right, so we have 1, 2, 3, 4 information pages. I'm going to cruise through this. This is the activated complex, and what that is, it's in your definitions. It's a transitional state between the reactants and the products. Okay, so we have a activated complex here. Boom, activated. All right. All right. The transitional complex is a short-lived, very unstable species that is the intermediate between the reactants and products. I enjoy changing words around. All right. So the activated transitional complex contains the highest amount of energy of all the species in the reaction. Its position at the top of the activation energy barrier is also represents the threshold energy as illustrated below. Here's your threshold energy. Okay, its position at the top of the activation energy barrier also represents the threshold energy. Okay, so what are you looking at? The activated transitional complex contains the highest amount of energy transitioning here from reactants to products. All right, transitioning. All right, so what do you call that? This thing starts with an A. Sounds like activated. All right, so next page. Really quick one. Good. In our second to last information page, you have some questions in here. Technically, we're right here. We have labeling. You know you love labeling graphs, don't you, by now? What is E? What is A? What is B? What's C? What's D? And what's E? So you should be able to label what the activation energy is. All right, hint, hint, hint. All right, the activation energy. Boom, I'll give you B here. Boom. All right. So moving right along, I don't really need to tell you those answers because you all know it by now because I'm such a good information facilitator, right? All right, thermochemical, make sure I'm on the right page. Actually, this is second to last. Thermochemical equations and enthalpy diagrams. All right, when this is a combustion reaction, notice you have a negative explosion here, giving off kinetic energy, making things move, and some forces generated as well as heat. Specifically, the combustion of 1 mole of methane releases 890.4 kilojoules of heat energy. So it gives off. The information can be shown as a part of the balanced equation. Yay! The equation tells us that 1 mole of methane combines with 2 moles of oxygen. 1 mole, there's a 1 here out in front, 2 moles of oxygen, to produce 1 mole of carbon dioxide. All right, that's what's produced here, and water. 2 moles of water, so the change in enthalpy is given. Heat, in this case, can also be written as a product of the reaction. Notice that if the release of energy is written as a product of a reaction, there is no need to include the negative sign. Wow. So if it adds into 890.4 kilojoules or given off as, so they're saying they're writing it in. See, they did this. So plus, it's in the products. That means it's giving off, even though it says plus here. If it was a reverse reaction, you're adding it into the reactants now. But it's in the product, so negatives or positives aren't needed. So don't get that messed up, because that's an easy one. Because they'll ask you, is this an endo or exothermic reaction? Since the heat is given off or added at the end, that is an exo given off reaction. And then you have a representation of the graph. You notice that heat is put in, because you're going from right to left here. All right, so you got the products here now. See that? And the reactants here. So now we're going backwards in the equation. This is going forwards, and that's the reactions there. And we have another video. It's a 4-minute one. That's a pretty short one on enthalpy. And I'll give you some ideas on how to go from reactions and how to possibly look at how to make a graph from it, or vice versa. All right. You notice how they just took the combustion reaction above and they made it here. This is the reactants side from left to right. That means they're adding in some heat energy, and that basically means that that's in the system now. So that is putting energy in. That's endothermic. All right, where are we at on the informational pages? The last one. Of course, this wraps it up. The lesson summary, we've learned that potential energy diagrams show how the potential energy changes during reactions. We labeled each section. We've did the activated. We did a bunch of stuff. So exothermic gives off, and the products will be negative as far as the amount of kilojoules. Endothermic is you're putting energy in from the products and reactants, and that's a positive kilojoules or enthalpy change as far as energy put into the system. The activated complex is positioned at the top of the activation energy barrier. Delta H, heat of a reaction, or the heat of the change in heat, measures the change in the enthalpy of the reaction. The enthalpy is the sum of all energy in a chemical system. The system involves the reactants and products in the reaction. The surroundings are everything else. Let's read that again. This lesson, you've learned that the system, all the species contained in a system, involves the reactants and products put together in the reaction. The surroundings are everything else. Like if you have sunlight, that's kind of everything else factoring into that. Kind of like a photosynthesis equation. You never see sunlight in that equation, or soil, or anything like that. Or the only thing you see is the molecules involved is water and oxygen and glucose and stuff like that. An endothermic reaction absorbs heat from the surroundings. An exothermic reaction releases heat to the surroundings. All right, so now we're finished. Your lecture is done for Wednesday, December 1st. Historical. All right, so as I close this out, we're going to look at my favorite monologue by, my favorite guy, Bill Murray, who is doing Scrooge today, and we're going to, have this gone through. So basically, I get it now. This is the monologue, basically. If you give, then the miracle can happen to you. It's not just the poor, the hungry. It's not just the, everybody has to have this miracle. It can happen for you. I believe that now. If you believe, these are people having trouble making their miracle happen. You have to take a chance. Okay, that's enough. All right, that's my monologue. Anyway, guys, that's your lesson for today. And of course, with our spirit of giving and doing that, I'm going to end this off with happy rest of the December. I like to do my themes. This is going to be December, Happy Holidays month, and those kind of things. So, again, let me know if you have any issues. And that was 11.2. And I hope you all enjoyed, my indulgence here. Take care.
Come on, just over here. All right, that's no good. Come on, let's try the other side of the theater. Come on. All right, how about just the men? Come on, just the men. All right, the real men. Let's hear the real men. All right, the women now this time. No, the real women. You know who you are. All right, you, who was making all the noise through the whole movie. My brother, the king of Christmas.